throw them at you. There you go. Okay, let's get started. Happy Monday. Any questions about PA3, which is about functions, about the midterm on Friday? Anything else about the class? Any questions? Questions? Yeah. I'm not going to ask specific questions from the readings. The best way to think about the midterm and what I want you to know is I want you to now have skills to be able to relate an implementation of a compiler, things about C code in a runtime, handwritten assembly instructions, right? I want you to be, like a definition of concrete syntax, right? I expect you to be able to relate all of those things, talk about where errors happen, right? Is the error a static error or an error that happens while it's running? What's the behavior of these things? What if we pick a different representation? So the best way to think about the midterm, and if you look at the past final that I posted on Piazza, is think of the midterm as kind of like a handful of these worksheets that we do in lecture with fill-in-the-blank kinds of things and questions about their behavior. That's the best way to think about it. And one of the reasons I like to do these worksheets in class is because these are the kinds of questions I really care about asking, so you get some practice with the format of things that I do on exams. So expect to see some OCaml code and some stack diagrams and some assembly instructions and be asked to fill in the blanks and answer questions about behavior. Other questions? Okay, cool. So there's two things I want to do today. One is I promised you last week that I would show you why this calling convention we're doing in class has advantages over the standard way C's calling convention is set up. So the main example that's on your worksheet is going to get at that. And the other thing I want to do is just talk about extending this calling convention to 2 arguments, just so we can have the examples of that on the screen. And also, it's really hard to see the reason this calling convention is better unless we can write programs with 2 arguments. So I wanted to add a second argument to our definitions, and then talk about the consequences of that, fill in the implementation for it, and then talk about why this is particularly good. Okay? The program that I have up here, this definition of I just wrote a function called add, and it just adds its 2 arguments together, so we could sort of have the simplest possible 2-argument function. This isn't on your worksheet, but the code on the right-hand side is on your worksheet. This code on the right-hand side is on your worksheet. And I want to highlight a few things. So first of all, here there is a new kind of definition that I added that's called def2. It's just a function that has a name, 2 arguments in a body, instead of a name, 1 argument in a body. Right? So we'll be able to talk about how those 2 arguments work. Aside from that, this compile def is exactly the same as it is in the code from Wednesday and Friday last week. And so the 2 things I want to talk about is, given that we want this code to generate this sequence of assembly instructions, there's 2 blanks here. One for what the environment should be when we compile the body, and then one for what we should use as the stack index when we compile the body. Okay? So those are the 2 blanks here. And I want to tackle those one at a time. So I want you to first focus your attention on this blank. Given that we want to generate that code, what should the environment be when we compile the body of this function? What should the environment start as when we compile the body of this function? I'm going to write some answers on the screen in a minute, but I want you to think about it without answers first. Then I'll write some answers here, and we'll do a clicker question for it. Okay? So talk about this for a minute, work through what do you expect the environment to be here? Sorry, this is gonna disappear for a second. My pen just decided it didn't want to. Hey, look, the midterm. Cool. There we go. My pen just decided it didn't want to write on here for a second. Yeah, there we go. Okay. All right. So some possible answers here. And if we think about the type that we expect the environment to be, we should be expecting something mapping from arg1 to some number and something mapping from arg2 to some number, right? We might have, for example, that arg1 is at address is stack index 2, and arg2 is at stack index 1. We might have that arg1 is at stack index 1, and arg2 is at stack index 2. Might have that arg1 is at index 0, and arg2 is at stack index 1. Or 1 and 0. So there's 4 interesting options to think about. Which one, did you come up with one of these, or answer for, if you came up with one of these, I'll leave an E for something else in case someone says, no, something else is what I had in mind. Okay, 5, 4, 3, 2, 1. Talk about this for about 30 seconds now that the answers are up here. Because you're fairly split, so I think talking about it will help. And one thing to talk about is there's a bunch of locations in the generated code. Which of these correspond to the arguments? Which of these correspond to the arguments? Okay. All right, click in again. Click in again. Okay. 5, 4, 3, 2, 1. Okay. So the way to think about sort of matching all these things up in your mind is, well, if we look at all the addresses that are used in the body of this function, 2 of these addresses are going to have to correspond to looking up x and y, right? Looking up the values of x and y so that we can add them together. And when we look up an identifier, we use a memory address for it and move it into EAX, right? So that these 2 spots definitely correspond to looking up variables and putting them in EAX. And we know from looking at the compilation of plus that the left-hand side gets moved first and then the right-hand side gets moved later. So the EBP minus 4 line must correspond to x, and the EBP minus 8 line must correspond to looking up y. So that must mean that based on the way we do our arithmetic for looking up stack indices, x must be at index 1 and y must be at index 2. So answer B here is the answer because what's happening is we're saying at the beginning of this compilation of this function definition, we expect that x is going to be 4 bytes above EBP and y is going to be 8 bytes above EBP. That's the assumption that this function definition makes. Later when we call it, we'll need to make sure that's true, right? But setting up the environment that way generates this code that's going to look for those variables at those locations. Any questions about why that is, about why those things correspond to one another? Why that makes sense? Questions about that? Yeah. Well, I'm sorry? Which parts are related? So these lookups of x and y are related to these lookups of EBP minus 4 and EBP minus 8 are related to looking up x and y and plus, right? And then the arg1 is going to be the string x and arg2 is going to be the string y. And so those things being in the environment are what make the body generate this code. So those are sort of the 3 related pieces. So I was just asking if there's any questions about why those pieces are related or how we got to that answer. Okay, cool. So let's fill in the next blank. So let's next focus on this blank. Okay, this blank here, right? And this is, just to be clear, this is the stack index position for like the starting stack index we should use when compiling the body of the function definition. Okay? So the starting stack index we should use when compiling the body. So think about this for a minute, and I'll put some answers up in a sec, but I want you to think about it without having answers in front of you first. Okay? So think about this for a minute. What goes in this blank? Right? The type is int, but what number goes here? Oops. Okay, pick a first round of answers here. Five, 4, 3, 2, 1. Okay, talk about this for a minute. What and why? What and why should be used to fill in this blank? Okay, clicking again. Clicking again. Okay. Five, four, three, two, one. Okay. Someone want to give a reason for picking A? A reason for picking A? A reason for picking A? I think there's good arguments for several of these. Although there's only one that I'm going to end up calling right, but there's good arguments for some of these. Reason for A. Reason for A. There's 21 of you. 21 of you picked it. So it's pretty split. So there's no, I mean, people didn't really like D or E, but fairly split across the others. Reasons for picking A. Picking A. Because it's like the new thing. We talked about stack depth right at the end of class on Friday, and it's like the new thing, so we're probably going to use the new thing. One reason. So A and B. So actually, it's worth asking, like, what does depth represent here? So we said let depth equal stack depth of body. What is, can someone just describe sort of what depth represents, like in English? What does depth mean here? What's depth going to be like here? Yeah? The amount of stack space we need to store local variables to do the computation. So is there something in the assembly already that corresponds to depth in the generated code that corresponds to depth or came from depth? Something in those instructions? Came from depth? Yeah. The first subtraction. And we can see, because down here in the code, right, we definitely have a use of depth right here in the code, right? So that sub ESP8 is coming from this use of depth. Depth was 2, and so that's where that's coming from. And so if we think about the sort of corresponding stack diagram to at start of add, right, which is, we can think of as during add, right, sort of while add is doing all of its work. Really what the situation we end up in is that we've subtracted 8 from ESP, so ESP is pointing up here, and these are going to be like the local vars of add, right, and we've made space for those. And depth was talking about the difference between the top of the stack where the last argument was and the place where we want the stack to go to have enough room for the local variables. That's really what depth was referring to. And when we pass in the stack index to body, what we're trying to represent is where in the stack should we start allocating local variables? Like, where's the first local variable? That's always what stack index meant when we passed it in to compile an expression. It meant here's the location at which you should put the first variable you see in a let, or the first temporary storage you need for a plus. And then as we go into nested expressions, we'll keep incrementing the stack index and using more and more space. So that suggests that what we pass in right here, right, what we pass in this blank that we're trying to fill in right now, should represent the address or the difference or the index from where EBP is, because EBPs are offset, to where the first local variable is. This should represent how many words there are between EBP and the first local variable. And the first local variable, if we're sort of counting up in the picture, the first local variable is this spot, right? This is the first one. We made space for 2, but this is where the first one would go. And that's 1, 2, 3 words above EBP. That's 3 words above EBP. In fact, that's where EBP minus 12 is coming from. The temporary storage for the left-hand side of the plus is going in EBP minus 12. That's stack index 3, right? Because 3 times 4 gives us 12. So it makes sense to use 3 here because that immediately hits the space that we've set up for the local variables and starts allocating them into these addresses that go up in the picture. Okay? If we use 2, we'd have a problem because we'd overwrite one of the arguments with the first temporary storage we used in the function. So 2 wouldn't work. And depth minus 1 are kind of interesting because it depends how they relate to the number of arguments. So they're just sort of not the right kind of thing to be using here. Because they're what we use to decide how much space to make for local variables. But the starting stack index for the body is about how many arguments there are. Because we want to not start putting our local variables in the argument space. We want to put them starting right above the argument space. So 3 is the best answer here, and it's 3 because in this calling convention, EBP is pointing at this return address, then we have 2 arguments, then we start this local variable space. So that's where the 3 is coming from, right? In your compilers this week, which are going to have a variable number of arguments, right? They can have a list of arguments. That means the starting stack index is going to be somehow related to the number of arguments that the function definition has. Because if the function definition has 5 arguments, when we compile the body, we shouldn't start using space in those first 5 words, because that's where the arguments will be. You just start at like index 6, for example. Okay. Yeah. So you said, can you draw a diagram to represent the stack when we start compiling body? So I think that is, the way to think about this is the at start of add picture here is the way we should think about the stack when body starts running. And so when we think about compiling the body expression, right, what we should have in our minds is the caller set things up, right? This was the app compilation should always set up this structure when it calls this function, because it's going to push the old EBP, push the return address, and then move the arguments onto the stack in order. And now the function definition gets to assume that that is the state of the world at the beginning, right? And those assumptions are what's making X be stack index 1 and Y be stack index 2 and the start of body be stack index 3, right? The start of the local variables be stack index 3, right? And information about body told us to subtract 8 from ESP, right? But all of this is based on the assumption that we're getting something in that shape, the at start of add shape. Did that answer your question? Yeah? Okay. Any other questions about this? Filling this in? Okay, so you can think of this as sort of one step towards generalizing the calling convention we had to a full list, right? We went to 2 arguments, not to a full list of arbitrary length, but that's sort of the first step. Now you can see that one way to set this up is to have the arguments being put on the stack in order that they appear, and then using this, this strategy for the initial environment to make sure that you look them up in the right order. Cool, okay. So the next thing I want to talk about is there's this function that we talked about very briefly at the end of class on Friday called stack depth. And that's at the sort of bottom right of your handout with all the compiler code on it, called stack depth. And there's a blank in it for the EAP2 case. Okay? And the EAP2 case is just like the EAP case we talked about last week, except it has 2 arguments, right? So it has an expression for argument 1 and an expression for argument 2, right? And so the question I have for you is, what should go in this EAP2 case for stack depth? And the way to think about this, you can, I put the other cases up here so you can compare to them. The question is, how much stack space does arg1 take up when we evaluate that expression? How much stack space does arg2 take up when we evaluate that expression? And do we need any temporary storage, like we need temporary storage for plus to keep track of stuff? And so I've commented out the body of some of these other expressions because we've seen them before and the code wouldn't fit on the handout or the slide. But I have all the code for EAP2 here. All the code for EAP2. It's a little different than some of the stuff we've seen before. In particular, there's a new argument here called TC. We're going to get to that in a minute. We're not going to think about that for sort of what we're discussing here. It won't affect what we're discussing on this screen. I just want to point out that this is a little different. If you think of TC as always being false, then you get back the compiler that we had on Wednesday and Friday. We'll get to this in a minute. But the question I want to ask now with this on the screen is, what should go here? How much stack space do we need while we're compiling an application? How much stack space do we need? How much space do we need to set aside? This is going to contribute to that value of how much we subtract from ESP at the beginning of a function, depending on how many applications are in the body. So think about this for a minute. How much space do we need for an EAP2? I'll put some answers up in a minute. Okay. Oops. There we go. Pick from these. Five, four, three, two, one. All right, talk about these answers. Talk about these potential answers and where they might be coming from. Okay, click in again. Click in again. Okay. 5, 4, 3, 2, 1. Okay. All right. So nice. Got some consensus here. So one way to think about this, and the thing we mentioned at the end of class on Friday, but we said it pretty quick. I said it pretty quickly, and I was over time, so I want to highlight it again. Is that the place to look for how much stack space a particular expression is going to need, sorry, the place to look is its sub-expressions, how much stack space do they use, and any stack space that the expression itself uses for temporary storage. Those are the two things that combine for everything the expression could use. So we should look at the recursive calls and anything the function does itself. And so in compiling EAP2, we have the recursive calls for arg1 and arg2. We have these two recursive calls. And when we compile arg1, we use si as the base stack index. But when we compile arg2, we use si plus 1. So when we use arg1, it's going to use up some amount of space on the stack to calculate that intermediate argument value. arg2 is going to use some amount of space, but it's going to start even higher on the stack than arg1 started. So whichever one of those is bigger, but keeping track of the fact that arg2 starts higher, is the one that we want. And C and D, answers C and D, both capture this idea that the stack depth that we use for arg2 is going to start higher. So the deepest we go in terms of stack indices is going to be one greater than whatever we use for arg2. So that's one contribution. And then the other place we need to look is any temporary storage that this expression uses. So the two places where we use temporary storage in compiling EAP2 are for stackval si and for stackval si plus 1. It's a lot like plus, actually. We're storing the two argument values onto the stack, and then we're using them later, right? So the same way plus needs to store the intermediate values just in case there's nested expressions and we overwrite EAX. EAP stores these intermediate values. And we use SI, and we know like SI is available because we always have the current stack index available, but we also use SI plus 1. We also use SI plus 1. And so we need to take that into account here. And this has a nice result if we pick D, so this plus 1 takes that into account. This has a nice result that you can see sort of naturally that the minimum that we could get from this is 2, because we're taking the max of something and something plus 1 and then adding 1 again, which sort of naturally corresponds to having these two arguments that are going to get saved on the stack as well. So So that's the answer that fills in correctly here. And really what I did to get that is I just sort of tracked the recursive structure of the compiler and looked for where we were adding to SI and used the recursive structure to say, well, it's going to be whatever we use in arg1 and arg2, and then adding in these specific spots. Yeah, so we could be smart in a few of these cases. In this case in particular, it would be not a good idea to keep the first argument in the AX, because then when we're evaluating the second argument, we might overwrite it. But there might be no need to save the second argument onto the stack. Yep, so there's actually a smarter way to compile this, right, where we would just leave the second argument in the AX, not save it to the stack. And then we would avoid having this sort of +1 at the very end, and we'd avoid using SI +1 here. So that's definitely possible. I wrote this way in part to make it clear that we're not doing anything particularly more sophisticated than with plus to compute the arg1 and arg2 of this. The only interesting thing that's happening relative to what we've seen before is setting up the stuff for the calling convention. So that's why I did it this way, but you're absolutely right. And when we get to talking about optimizations, it'll become clear that there's several decisions we could make in structuring the compiler that would save some of these things, in some cases. Okay, so that's what we'd fill in here, and now we'll properly account for the space that EAPs take up locally to a function in calculating the stack depth of a function spot. Okay. And then the rest of this code is very similar to what we had on Wednesday and Friday, just that we're storing these things to intermediate space before pushing them onto the stack. Okay. So I want to talk a little bit and to make you read the EAP case code. So here is this function sum, written in a very direct style. It's basically the same sum function that we had on in class on Wednesday when we first talked about a recursive function. And all I want you to do for this is read the compiler and come up with what instructions are going to go in these two spots. And this corresponds to, in the compiler, there's a local variable called init and a local variable called after. And these refer to things that happen before the function call and after the function call. And so I want you to look at init and after and see what instructions are going to be generated for this compiled version of sum. So take init first. Let's focus on first init. And in this case, it's useful to actually look at compile def and look at e to i's and see how this new TC variable, new TC parameter is being used, because that affects what goes in init and after. So try and trace that through, figure out what's going to go here for init and what's going to go after this call. And I'm going to ask the question here in a different way than asking what instructions should go here. What I want to ask is TC true when compiling this expression? I'm going to write it in a different color and then circle it so I'm clear which one I'm talking about. When compiling sum of plus and negative 1, right? When I'm compiling this expression. Because in EAP2, there's all this stuff about is TC true, then we do one thing. So the question is TC true when compiling this? Yes, it's true. B, no, it's not. Is it true when compiling that expression? And I'm just drawing this stack of what sum is going to look like while it's running so I can talk about it in a second. But is TC true when compiling this expression? Yeah. So we're gonna, what I want to do is not describe what it means. I want to say what it does, and then I'm going to define it, right? What I want you to do is trace this code and see why the heck it would be defined this way, and then sort of define it, right? So I'm explicitly, much like with env, I did not tell you what env was until we worked with it, and then we defined it. That's what I'm doing here. So I just want you to trace the code, right? If there's a bunch of trues and falses being passed around for TC. What does it end up being when we get here? Five, four, three, two, one. Okay. Talk about this for a minute, and then I'll open it up again. Okay, clicking again. Clicking again. Okay. 5, 4, 3, 2, 1. Okay. All right. So let's trace through this. So the place to start is to ask what it looks like, what TC's value is when we start compiling this definition, right? So when we look at this whole body of this function, right, the whole thing, right, which is the body of some definition. TC is true because it says so in compile def, right? If you look at the code of compile def, it says we're going to compile the body, we're going to pass in the environment that we decided on earlier, and then we're just going to pass in true for TC. So when we're processing this whole body, it's definitely that the parameter TC is true, right? Then we need to think about how TC changes as we visit each sub-expression. So the next kind, the kind of expression that's in the body is an if. And so we can look at how the TC parameter is passed through for an if. So in the bottom left of your sheet with the compiler, EIF says, well, the conditional we pass in false. Then in else we pass in whatever the current value of TC is. Then in else branches we pass in whatever the current value of TC is. So if we're sort of drilling down to this question, it's definitely true when we start compiling the then branch. It's definitely true when we start compiling the then branch. The then branch is a plus expression. So then we need to ask, well, what does plus do when we do this? Well, plus says, let's compile E1 and E2. When we compile E1, let's pass in false. And when we compile E2, let's also pass in false. Right? So if you look at the E plus case, so I guess I can scroll up and circle it here. Right? In the E plus case, what I'm looking at is here and here false is passed in for TC when we process the E1 and E2 in a plus expression. So false is passed in. So that means by the time we get to this sum expression that's nested inside a plus, which was in an if, which was in the body of a function, the value of TC is false. It's not true. Because when we compiled the plus, we said, now we're going to have to define this in a second, but when we compiled plus, we said, no, this is not true. We're just going to make it be false when we compile either side of a plus expression. So this ends up being false, which tells us that init is false. So we're going to use the else cases for defining, which means that we're going to use the else cases for init and after. Right? So init is going to look like the same calling convention we saw last week. We're going to push EBP and then push some return address, which we called after call. So I'm just going to write it as after call. And then after is the two instructions, which are after call and pop EBP. Okay. So this is just sort of a reminder of the calling convention we've seen before. I drew here this picture of what's going to happen when we call this. We'll keep having these old EBP addresses, then the return address, which is always going to be after call during these recursive calls, then the two arguments. I just wanted to only have one version of EAP, so I had two arguments, but we're not using the second one. So we'll have 3, then 2, then 1, then eventually it'll get to 0 and hit a base case. This is what the stack looks like during all these calls. Okay. So let's go on to the next example. So this is the example that's on the right-hand side at the bottom. Okay? And to break the suspense, the interesting thing about this example is that in this case, this sum, if we trace it through, TC ends up being true. Now, I'm going to define what TC means before we step through this example that's here. Okay? So TC is this is a vocabulary word, so it doesn't mean anything until we define it. TC means tail call, which is like, okay, now there's like one more vocabulary word. And the intuition behind what a tail call is, okay? The intuition behind what a tail call is it's an application where the only thing we do with the result is return it. Okay? So in this case, right, we have this recursive call to sum in the then case of an if. There's no more work to do with the result of this recursive call after we're done. It just is the return value. It's the return value of the if and the return value of the function. Right? There's no more work to do after this is done. And if you compare that to the other sum, the recursive call was nested inside a plus. We needed to take the answer for that recursive call and add it to something else. There was more work to do with that return value before we were done with the current function body. And by keeping track of, this just required a little bit of our knowledge of where we would use the value from a function call after, or where we would be done after doing a function call. That's how we figure out where to put the trues, falses, and to pass the value of TC through. That's how I made those decisions in the compiler, right? In the then and else branches of an if, that's the last expression it's going to evaluate for that if. So if we have an application there, it can be a tail call as long as that if was also the last expression in its context. And so that tells us that this application is maybe somehow special. We don't need to store its answer anywhere and then use its answer for something else, right? It's just going to be returned from the current function that we're in. That's all that's going to happen with its answer. So that means we're going to, in the implementation I've given, if TC is true, this is a much simpler set of instructions. This is instead of pushing anything here, we set ESP back to where EBP is. Just set ESP back to where EBP is. like just moving it back, ignoring all of the local space in the arguments. And then after is the empty list, so there's nothing here. There's nothing here. What the heck does this mean happens when we do this call? Like what does this mean in terms of a picture? So on the last slide, I drew the stack growing up, 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 because we just kept pushing and moving EBP up and changing the value of EBP. Here, we're going to start with old EBP. So I'm just going to draw this picture and then we'll wrap up. Old EBP and the return address. And then we're going to have these arguments like 3 and 0 are the arguments the first time. NESP is somewhere up here right before the call, and EBP is always pointing at the return address. And what happens when we do this call is we move ESP and EBP all the way back down to be pointing at the same spot briefly. And then we start pushing the arguments to the recursive call from here. We just overwrite this stack frame. So this ends up getting 2, and in this case, 3, right? Because those are the values we get for subtracting 1 from n and adding n to 0 for this first call. So we move everything down. ESP just moves up with these pushes as normal, and EBP stays down here. So instead of creating a new stack frame, right, instead of growing a stack frame on